Hello everyone, my name is Haru from Deakin University. Welcome to my tutorial about a very important data structure in computer science, a red black tree. Today, in this video, we will explore together what is red black tree, why we need the red black tree, the properties of it, and we will focus on the insertion method in the red black tree. So let's start it. So before we learn explore about the red black tree, we need to understand the current problem with the normal binary search tree. So in normal binary search tree, when we insert a value, the smaller value is go to the left and the larger value go to the right. But this is only work well if the tree is balanced. So what happens if we insert a, a sequence of shorted value? So for example, in the ascending order, like 1, 3, 4, 5, it may become a linked list like this rather than a tree. So in this case, the height of the tree becomes very large, and the operation like search or insertion can takes the O(n) time complexity. So the key problem here is how can we keep the tree balanced after inserting or deleting a node. So that is why we use the balanced binary search tree. So one solution is the A-field tree. A-field tree is a self-balanced binary search tree. So it's used the values called balance factor. The balance factor is computed by calculating the difference between the height of left substrate and the right substrate. One of the benefits of A-field tree is that it's a very strict balanced binary search tree because it tends to keep the height of tree as small as possible. So because of these features, the height of the tree is usually smaller than the red black tree, and the searching methods can be performed very fast in a low time complexity. But the A-field tree is also have a key disadvantages because it is very strict. So normally when we insert or delete any nodes, it may require more rotation to restore the balance. So A-field tree is good when we have many search operation, but it may require more maintenance when there are many like insertion and deletion as well. Alright, so another solution that I want to introduce to you is the red black tree. So the red black tree is also a self-balanced binary search tree, but it's not strict as a field tree. So we can say the red black tree as a quick balanced binary search tree or the almost balanced binary search tree. And one of the very special feature of the red black tree is that each of node has a color. It can be either black or red as the name. And instead of using the balancing factor like in the A-field tree, in the red black tree, we do balancing using two methods like recoloring and rotation. So because the red black tree is more flexible, so it is often more useful when we work with some scenarios that require more insertion and deletion operation. And because this is not because it may be not perfect like a field tree, but it is useful and because it needs less strict maintenance. So to maintain the balance, the red black tree is had to follow a lot of properties, and we have 5 important properties of the red black tree to maintain the balance. The first one, each node is either red or black. The second one, the root is always black, and the next one, if a node is red, its children must be black. This means that we cannot have a two red nodes that directly connected as a parent and a child. And the next one is every leaf or the new node is considered as black. As you can see on the picture, all of the new node is black. So normally when we draw a red black tree, we don't draw a new node, but we always consider there is a the null node there and it's black. The final one is a very important. So for every node, all paths from that node to its descendant leaves must be contain the same number of black nodes, and this called the black haze property. And this rule is help the red black tree can stay almost balanced or quickly balanced. So the haze does not become too large, but it's not perfect like the Eiffel tree. So in this part, I will introduce to you how to insert values or nodes into the red black tree. So when we find a position to insert a node into a red black tree, it is similar to the normal binary search tree, but there is some important points how to consider. So first, the new node is always red. So why? So why the new node is always red but not black? So let's move to the properties of the red black tree. So here we can see that if we always put the node as black, it will immediately break the final properties, the fifth property. And if we break the fifth property, we have to draw the entire of the red black tree again. But if we put a node as red, we can potentially break the property 2 or the property 3, and it is very to fix. Let me show you in the next section. So the next point is if violation occurs, perform balancing by two methods, recoloring and rotation, or we have to use both. And finally, there's many scenarios when we insert a node into a red balance tree, so we need to focus on some value. First is the node n, that the node that we just insert into the red black tree is parent p, the brain parent g, and the uncle u, as shown as in this picture. So if we insert 25, its parent is 17, the grandparent is 13, and the uncle is 8. So in the next session, I will show you some scenarios when we insert a node into a red black tree. So let's get started with the first scenarios when we insert a node into a red black tree. So the first scenario that we may come is the root is red. So here, if the root is red, the solution is very simple. We just recoloring the root into the black, and that's we done. And then let's move to the second scenario. So in the second scenario, the parent is red and the line GPN occurs and U is red. So let me show you an example. So in this graph, we insert 25 is red and the parents B is red, and there's a line from grandparents, parents, and the children, and the uncle of 25 is 8 is red as well. So the solution is very simple. We just recoloring all of the parent, grandparent, and the uncle like that. And then you have noticed that the root 13 is red, so that's come to the first scenario that the root is red. So very simple, we just recoloring the root into black, and then we done. And move to the next scenario. So the next scenario is that B is red. There's also a line between G, P, N occurs, and but in this case the uncle is black. So I will show you an example. So we also insert 25, and the parent of 25 is 17 is red, so both of them are red, so it violates the properties of red black tree. And there's a line from grandparent parent to the children, and the uncle of 25 is A is black. So here we have to recoloring the grandparent and the parent. So 13 and 17 node, they should be recolored like that. And then the next one, we have to do a single rotate on the grandparents 13. So after we rotate do a single rotate on the grandparent, we're gonna have a new graph. And then we check the properties again, and then we notice that is satisfy all of the properties of the red black tree. So that's why. So we move to the final scenarios. So the final scenario is that we have, let me show you the example. So we have B is red, and so we have we insert 16 into the red black tree, and the parents B 17 is red, and there is a triangle occurs from the grandparent, parent, and the new node, and also the uncle is black. So what we should do here, so what we should do is that we do the rotation on the parent 17. So after we do the rotation on the parent, we're gonna have a graph like that. And then what should we do now? So as you can see in the new graph, we have two red knot here. So we not allowed to have a the both parent and the children as the red knot. And also there's a line from G, B, and N, and the uncle is black. So this is case 2 as we did before. Just follow the instruction in case 2 and then redraw the red black tree again, and then we can miss the all of the properties of the red black tree. Okay, now I will show you how to insert a sequence of nodes 1, 2, 3, 5, 4, and 6 into a red black tree. Before we start, we have to remember that when we insert any node, we have to initially set them as a red node. So let's start with node 1. So the first one, node 1, and it's in case 1. The root is red, so the solution is we have to change the root from red to black. So we change 1 into black. We check the properties of red black tree again. It's nothing or violence. So we done with the node 1 and we move to node 2. So 2 is greater than 1, so 2 is the right child of 1. Then we check the properties of red black tree again, and then we say, okay, all of the properties are satisfied. So we can move to the next node, node 3. So in node 3, 3 is greater than 1 and 2. So 3 is the right child of 2. And then at this stage, you're gonna notice that 2 is the parent and its children 3, they are both red. So it's valid the properties of red black tree. And also the children, parent and the children 3, parent 2 and the grandparent 1, they are from a line. And the uncle is black, so it is in case 3. So in case 3, first we have to recolor the parent and the grandparent. So we recolor 2 from red to black. Color is that one from black. And then we recolor 1 into red. And next, in case 3, we also have to perform a rotation on the grandparent. So here we perform a black rotation on the grandparent. So after black rotation, we're gonna have a new node with, so 1 is become a black child of 2. Yes. So this is a new red black tree, and then we have to check the properties of red black tree again, and then we say okay, so all of the properties are satisfied, so we can move done with the node 3, and then we move to the next node, node 5. So in node 5, 5 is greater than 2 and 3, so 5 become a right child of 3. So here the right child of 3 is 5. and then we violate the reflectory properties again because 3 and its children is 5. They are both red. And what case are you in now? So 5, 3, and 2, the new node, parent and the grandparent, they perform alike. But the difference is the uncle is now bred, so we don't have to do the rotation. We just have to recolor parent, grandparent, and uncle. So 3, we recolor red into black. So 2 is red, so we recolor into, 2 is black, so we recolor into red. Maybe I did something wrong here. Sorry, this one should be 1. I'm so sorry about that. So 2 here is red, and then node 1 is red, so we recolor into black. Yes, so we check the red reflectory again, and we can see that the root 2 is now red. It in case 1, the root is red. So the solution is we recolor the root into black. So we color it into black 2. Then, so we check the red reflectory again, and then we notice that all the properties are satisfied. So we're done with node 5. So let's move to node 4. So in node 4, so 4 is greater than 2, 3, but it's less than 5. So 4 is the left child of 5. It has to be bred, and the property is bred again. So 5 and its children 4, they are bred. So let's see what case are you in now. So we can see that the children, grandparent, and parent and the grandparent, they are from a triangle like this, and the uncle are black, so we are in case 4. So in case 4, first we have to perform rotation on the parent 5. So after rotation, so rotation 5, so it's 4 become a children of the grandparent, and 5 become a bride children of 4. And then after the rotation, we can check the red reflectory again, and then we say that we can notice that the red reflectory still violate the properties. So because 4 and its children 5, they are both red, so we check what case are you in now. So the grandparent, parent, and the children, they are perform alike, and the uncle are black, so we are in case 3. So in case 3, first we recolor 4 and 3. So 4, we recolor it into black, and 3, we recolor into red. And then we perform a rotation on 3. So 4 is gonna be here, and then 3 become a left child of 4. Then we check the red reflectory again, and then we can see that all of the properties of the red reflectory are satisfied. So we're done with node 4, and then we move to the last node 6. So in node 6, 6 is greater than 2, 4, and 5. So 6 become a right child of 5. So 6. We check the red reflectory, and then we see that it also violates the properties because 5 and 6 are both bred. And what case are you in? So 4, 5, and 6, children, grandparent, parent, and grandparent, they are from alike, and the uncle are black. So we are in case 3 as well. So in case 3, we have to first recolor 5 and 4. So 5 bred, we recolor it into black. 4 is black, so we color into red. And we have to rotation on the grandparent 4. So after rotation, so 4 it will become, sorry, here 4, 5. So first 4 will be, the subgraph for it will become a left child of 5 after rotation here. Yeah, so then we have to check the graph again to see if there is anything violates the properties. And then we can see that the properties of the reflectory are satisfied now. So it means that we have done with the reflectory for this sequence. And in the next part is a time complexity analysis of the insertion method of the reflectory. So as we all know that the height of the binary search tree is log n. So the time complexity we use to find the position to insert a node is take all log n time complexity. But in balancing method, we have coloring and rotation. So in coloring, we use multiple recoloring. It can take up to the old log n in the work case. But in the reflectory, we use less rotation than the A-field tree. So it's nearly O1. But the total of the time complexity is O log n. So overall, that is all of my short tutorial today. So in this tutorial, you have captured some concepts of the binary search tree. So that is all of my short tutorial for the red black tree for today. So in this tutorial, you have catch up a lot of. So thank you for watching. This is all of my short tutorial today. So in this tutorial, you have gone a lot of concepts of the red black tree, like the definition, why we need red black tree, properties of red black tree, and you also have how the insert method in the red black tree work. We also have go through some example about insert a sequence of nodes into a red black tree. I hope this tutorial can help you beyond some concepts of data structure and algorithm. If you have any questions, please comment below. I will be pleased to answer all of your queries. Thank you.